Hi, everyone. Welcome to the seminar. Today we have Saba Ahmadi speaking our seminar. Saba is currently a postdoc at TTIC, hosted by Avrin Blum. Before TTIC, she was a PhD student at University of Maryland, College Park, where she was advised by Samir Kular. And she also spent a couple of years at Northwestern during her PhD. And Saba's research interests are in social aspects of computing, learning theory, and combinatorial optimization. And today she will tell us about learning, incentivizing improvement, and fairness in the presence of strategic agents. All yours, Saba.
All right, thank you. And thanks for inviting me. Okay, so I'm going to talk about learning, incentivizing improvement, and fairness in the presence of strategic agents. And this is a joint work with Hediye Behaqi, Avrin Blum, and Kezia Najita. Okay, all right, so I'm going to talk about 3 lines of work, and I'll start with strategic online classification. All right, so this is based on a piece of work that appeared at EC21. Okay, so here the goal is to learn a classifier when the data is provided by strategic agents. And for example, we want to decide who is loan worthy, who is not. And then, okay, so but like here, the agents are able to modify the way that they appear if it helps them to get classified positively, but like this modification does not truly change their qualification. And okay, so it's particularly challenging because the way that agents manipulate depends on the current classifier. So for example, here, suppose that we have like our classifier is this linear black line. And then so like if like maybe some of the agents are close to it, so they would move. The ones that are too far, and like are negative, they may not move. But like if we have a different classifier, maybe another subset of agents would move. And then, so it's also like particularly challenging in the online setting because there is like no distributional assumption. So we can't have like a training phase where we are like giving everybody a loan or like not giving anyone a loan so that agents have no incentivized to manipulate. And so like get some clean data and then learn a classifier and then like maybe change the classifier so that no one would manipulate. So basically like this lack of distributional assumption would make it more challenging. All right, so I'll first talk about the model in the setting. So it's an online binary classification problem. And so the data points are like in a d-dimensional space. They arrive one by one. And I'm going to talk about the setting where these original data points are linearly separable. So these clean, unmanipulated examples are linearly separable. And then, okay, so agents can manipulate their observable features at a cost per unit of movement if it helps them to get classified as positive. So basically they have a value of 1 for getting classified as positive and 0 for getting classified as negative. So for example, here, there's a cost per unit of movement. So let's say here is 1 over alpha, and therefore they would at least move for distance of alpha because that's as long as like their cost would be less than or equal to their benefit. So they would not move more than the distance of alpha because it would not basically justify their benefit in that case. And then, okay, so agents also know the current classifier at a given step. And so for example, if the classifier is deterministic, they would only move if it changes their label from negative to positive. And they would do it in the cheapest possible way. And this is because the agents are utility maximizers. So like their utility function is their benefit minus their cost. So they would only move if they receive a value of 1, and they would also minimize their cost. So for example, here this agent at the bottom is gonna move, is close enough to the current classifier, which is a black line, So it would move, and it would move in the cheapest possible way. All right. So I'll talk briefly about some related work. Okay, so I'll just mention a few related works. There's a lot of related work. So one is this piece of work by Hart et al. And they consider the distributional case, and like their cost functions are separable, meaning that, so it's like in a one-dimensional space, there is a cost of moving from x to x prime that is like proportional to the distance between x and x prime, and like moving in the negative direction is for free. Okay, so so the difference is that our case is online, and our cost functions are different. And another piece of work is, this is closely related, by Deng et al. So they have like an online regret model with convex losses, and they can handle the case of different agent utility functions. So for us, the cost functions, the loss functions are non-convex. So basically, the agents do not care about like their distance to the, like their dot product. Like they don't want, like as long as they get classified as positive, they wouldn't care about maximizing their dot product with the current classifier. Like all they care about is to get classified as positive. So our losses are non-convex, and they might even not be continuous. But on the other hand, we can only handle a case where agents have the same utility functions. Okay, so, and there's also a lot of other related work. I'm just mentioning a few of them here. Okay, so for the rest of this part, I will first talk about an algorithm that is used for online binary classification, specifically Perceptron here. And then I will show that, I will briefly go over it, and then I will show that why Perceptron would fail in the case of strategic classification. And I will show our algorithm. Okay, so just briefly about Perceptron, it's used for online binary classification when there's no manipulation. So specifically, I'm here just showing the realizable case. There exists a perfect classified W star. That being said, for the positive examples, X, the dot product with W star is at least 1. There's like a margin of separation. And then the dot product with the negative examples is at most -1. And then, okay, so the algorithm proceeds in rounds. At each round, you would see a new example, and then you would predict the label of the example using the current classifier W, where W is initially all 0. And then, so whenever a mistake happens, basically W gets updated. And then the way the W gets updated is like, if X is negative, W gets updated by subtracting X. So basically when Y is negative and then there is a mistake, W gets updated by subtracting X. And if it's like there's a mistake on a positive example, a W gets updated by like adding X. Okay, and then when the data is linearly separable, Perceptron can find the perfect classifier when the number of mistakes is bounded. Okay, so I will now show that why Perceptron would fail in the case that agents are able to move. Okay. So here is the example. So basically, so in this example, alpha is 0.5. So it means that agents are going to move in a ball of radius 0.5. And then an online sequence of examples would arrive. So first A arrives, and then B and C arrive alternatively and repeatedly. Okay, so let's see, what does Perceptron do? So initially it's all 0, and okay, so it's all 0 and would predict all positive until the first mistake is made on the first negative example, which is A. Okay, now W gets updated by subtracting A. So W becomes 1 and 0. This is the new W. Okay, now B arrives. B is on W, so the dot product would be non-negative. B would be classified correctly. Okay, now C arrives, but C is too close to the classifier. So basically, it's within a I said that alpha is 0.5 and distance is 0.5. So it can basically move, reach to the classifier and get classified as positive. So it would move, and then it would appear at in the cheapest possible way. So it would be 0 and -1. But like the point is that the algorithm would not see where it truly came from. All it would see is in its manipulated location, which is a 0 and -1. Okay, so C appears at 0 and -1, and then it gets classified as positive, but it's truly negative. So now W needs to get updated. It gets updated by subtracting C because C is negative. So W gets 1 and 1 now. Okay, so now we have W 1 and 1. And then, so now B arrives, but B is too far from W. So it has a distance of basically 1. No, it has a distance greater than 0.5, so it would not reach to W. It would stay put, but and get classified as negative. But B is really positive, so it would be a mistake. So now we need to update W. So we would update W by adding B. So W becomes 1 and 0. So now we are back to where we were. And now B and C just, we would just receive them repeatedly, and therefore the algorithm would make an unbounded number of mistakes. Okay, so this is why the perceptron would fail in this setting. And now, so I will move and talk about how to modify perceptron so that it would work in a strategic setting. Okay, and I will talk about two different cost functions. The first one is L2, and the second one is weighted L1. Okay, so first is L2. Okay, so in this setting, okay, so here the cost of manipulation is corresponding to the L2 distance between 2 points. And then again, alpha is the maximum distance that the other ones would move to achieve a positive classification. Okay, so initially, we will assume that alpha is known, but this assumption is not critical. It can be relaxed. But like just for the start, we're assuming that alpha is known. Okay, so this assumption is essential. We're assuming that the original data points, the ones that have not moved, those are linearly separable. Okay, so that being said, there exists a perfect classifier W star, such that for the positive examples, the dot product is at least 1. For the negative ones, the dot product is at most -1. Okay, all right, so let's go back to our example where perceptron failed. Okay, so in that example, this black line is a perfect classifier if the data points do not move, right? It gets B as positive, gets A and C as negative. But like, it's not a perfect classifier in the strategic scenario. So basically C is too close to the line, it would move, reach to the line, get classified as positive. So it would be a mistake on C, okay. But like what would work in the strategic case is to shift W star. So W star was a perfect classifier for the original data points. If we shift W star by a distance of alpha, so basically this use this line W star that X is at least alpha, then that would be a perfect classifier for the strategic case. And the reason is that so all the positives are still close to the dotted line, to this new shifted dotted line, so they would still be able to reach to it and get classified as positive, but all the negatives would be too far from it. So they would not be able to reach to it. They would get classified as negative, but we would get all the positives correctly. So what we really need to do is to find this shifted dotted line. Okay. All right, so let's see how we can do it. Okay, so this is now our strategic perceptron algorithm. Okay, so initially predict all negative until the first mistake is made on an example X, let's say W, and then put W equal to X. Okay, all right, so let's see. So like in the perceptron algorithm, whenever W is updated by adding some X tilde, like in the perceptron algorithm, the way that the proof works is that like it shows that two key properties hold, and those two properties would help to bound the total number of mistakes. And those two key properties are first that whenever an update is made, by adding X tilde, first the dot product of W star and X tilde is at least 1, and second, the dot product of W and X tilde is at most 0. So whenever these two key properties hold, the total number of mistakes can be bounded. So this is like we would want this similar properties to hold in our case in order to be able to bound the total number of mistakes. Okay, so let's see how, okay, so let's see just quickly, like how do these properties hold in the non-strategic case? Okay, so whenever a mistake is made on a positive example X, just let X tilde be X. Okay, so we know it's positive, and we know that W star is a perfect classifier. So we know that the dot product of W star and X tilde is at least 1. And then we were making a mistake on X, so therefore its dot product with W was negative. The second property also holds. Similarly, we can show that whenever we're making a mistake on a negative example by putting X tilde equal to minus X, these two properties would hold. Okay, all right, so let's see. But like in the strategic case, the problem is that the points are going to move, and then we only had this separability assumption, this W star dot Z is at least 1 for positive examples, W star dot Z for negative examples is at most -1. We had those properties for the unmanipulated data points. So after they move, these properties may not hold anymore. So like these first property may break. So we need to be careful whenever we're making an update. Okay, so basically the algorithm is like case by case. There are 4 types of mistakes. And then, so I'll just do some case analysis to show in each type of mistake how we're gonna find X tilde. Okay, so there will be 4 types of mistakes. Okay, so in the first type, okay, so let's say that, okay, so this is W is the, okay, so this is current W, and this is the current classifier, which is the shifted W. Because if you remember, I said that we want to find shifted W star. Okay, so basically at this round, our current classifier is shifted W. And then we're seeing a positive, let's say below W. Okay, so we know that it's too far from the current classifier. Its distance is greater than alpha. So it would just not move, right? Because why would bother moving when you're not getting classified as positive? So we just stay put. And then because it has not moved, then we know its dot product with W star would be at least 1. Because it's a true positive, it did not move, so the first property would hold. Also, it's like below W, so the second property would also hold. So all we need to do in this case is just to put X tilde equal to X, to just do the update using the original example. Okay, so the second case is that X is between W and shifted W. So in this case, it would be problem. Okay, so if we do the update using X, it would be problematic because the second property would not hold, right? It's X is above W, so its dot product would be positive. So it would be problematic if we update with X. But the good thing is that, I mean, this case would not happen because X is too close to the class to the dotted line, which is our classifier. Therefore, it would just move, reach to a classifier and get classified as positive. So we would never be in such a scenario where there exists an example between this solid line and the dotted line. Okay, and then basically this is the idea that we use for the case of unknown alpha. So like if you remember, I said that I will say that our algorithm for the case of known alpha, but we can handle the case of unknown alpha, and it's by simply like guessing alpha. And if we ever reach to a case where we see an example in like between the W and the dotted line, then we would know that our guess was too large, so we would not need to like fine tune our guess. So this is the essential idea for handling the case of unknown alpha. Okay, so the third case is that like we have an example X above the X is truly negative and it's above the current classifier. Okay, so let's see what would be the value of X tilde in this case. So we know that in this case, X has not manipulated because it already gets classified as positive, so it does not need to move at all. And then just by putting X tilde equal to minus X, the problem will be solved, right? Because X is negative and it's unmanipulated. So its dot product with W star is at most -1. Therefore, the dot product of W star and negative X would be at least 1. And also because X is above W, therefore its dot product with W would be at least 0, and therefore the second property with X tilde would also hold. Okay, so this case, we just need to put X tilde equal to minus X and the properties would hold. Okay, so this last case is a little bit tricky. So okay, suppose that we have like a negative point in like its true location before manipulation was between W and dotted line. Okay, but it's like too close to the dotted line, so it would move, reach to the dotted line, and because it's underclassified, it would get classified as positive, right? Okay, so now there's a mistake. We need to update W. Okay, so let's see. But we do not know where Z truly is, right? We do not know its true location. All we know is that it has came like from somewhere in this region and just appeared here. Okay. Okay, so in this case, what we would do is to shift X back to reach to the solid line and move in the direction of W. Okay, so because the agents would move in the cheapest way possible, then we know that like wherever it was, it has moved in the direction of W to reach the current classifier. So what we need to do is to shift it back in the direction of minus W. Okay, and then what we would know is that the true location was somewhere along this line, but we don't know exactly where. Okay, but like what we're gonna do is to, it's like overestimating the true location. Okay, and then what we're gonna do is to let X tilde be equal to minus X prime, where X prime is this point that we get when we're shifting back. Okay, so now, okay, so let's just show that these two properties would hold. Okay, so the first property, okay, so we need to show that W star dot X tilde is at least 1. We know that W star dot Z is at most -1 because Z was the original example and we had this assumption for the original examples. So what we can show is that throughout our algorithm, we can prove that it would hold that the dot product of W and W star would stay non-negative. Okay, so now basically the point is that, okay, so now we have these two properties, W star dot Z is at least -1, and the dot product of W and W star is at least 0. Okay, so basically, what we did was that we pushed X back in the direction of minus W to get X prime. So, and because the dot product of W and W star is non-negative, we have pushed it back further away from W star compared to Z. So if the dot product of W star and Z is most negative one, so would be the dot product of X prime and W star. And then, okay, so this holds, the dot product of X prime and W star is at most negative one. So the second property, so the first property would hold for X tilde. Okay, because X tilde is minus X prime. And then the second property would also hold because X prime is on W, so its dot product with W would be 0. Okay, so the two properties would hold. And then, okay, so basically that's still like what we did was that to show that in each of these types of mistakes, these essential properties would hold. Therefore, we can bound the total number of mistakes. All right, so that was for L2 costs. So for the case of weighted L1 cost, let's see what would happen. Okay, so here, what happens is that individuals can only move along the coordinate vectors, okay? And then, so here we can handle the case of known costs. Okay, basically when the costs are known, we can use the costs and the current classifier to specify what is the most cost-effective direction. Okay, so we would know that along which coordinate the vectors would move. So when was in the L2 cost, we knew that they would move like in the direction of W because that's the cheapest possible way. So here, depending on the cost along each coordinates and the current classifier, we can still be able to determine which one is the most cost-effective direction. And then basically we can change our algorithm to work for L1 costs when the cost of moving along different dimensions is known. But like when the costs are unknown, then we do not know in which direction the individuals would move, and then we cannot handle this cost. Okay, so we can only handle it when the costs are known. Okay. All right, so just to summarize the first part, we can do online strategic classification in a few scenarios where the L2 costs are known or unknown. And we can also handle the case of L1 costs where the costs are known. And like when I was explaining the algorithm, the W star was passing through the origin, but we can like relax this assumption. We don't need the true separator to really pass through the origin. We can handle it for the general case as well. Okay, and then in terms of like, okay, there's a question. Is there a range for unknown alpha? I mean, okay, so basically, I mean, you can, because it's like a binary search, you can start from like, I don't know, like put your alpha, like the maximum norm of the examples, like just say that is like the maximum that the examples may manipulate, and then just start from there and do binary search. But yeah, I mean, doesn't really matter because like at the end of the day, you just need to do binary search. Okay, and then in terms of open questions, okay, so our key assumption was that the unmanipulated data needs to be inseparable, and it would be interesting to relax this assumption? And also, what can we do for the case of unknown L1 costs? So, okay, that's for the first part. So I'll, if there are no questions, I would move to the second part of combining gaming and improvement. Okay. Okay. So, so I will. So the last two parts will be shorter. So, the first part. So here, it's like based on piece of work that appeared at Fork this year, and so here we are supposing that some directions are gaming, some are improvement. So for example, we want to decide who is loan worthy, who is not. But like, for example, like if a feature is like the number of credit cards, it's easier to game that feature versus if like some features, for example, taking a money management class, it's easier to like improve along that feature. So so yeah, we are like trying to like the setting is that some features are gaming, some are improvement. And then so the goal is to maximize the total number of true positives, which is the loan that we need to give to qualified candidates, subject to the number of false positives is at most some upper bound. So meaning that we're just giving a few loans to the unqualified candidates. Okay, so in this setting, even a perfect classifier can be suboptimal because it may not incentivize improvement. So for example, this linear classifier is a perfect classifier. It's separating positives from negatives, but like it's too far from all the negatives. So none of the negatives, like they can still move for a bounded distance, but they're like too far, so it would not make sense for them to improve, and reach the classifier. But like, if you consider this other green classifier, so it's like close to this negative example, and then so you would have the incentive to like move along the improvement dimension, reach to the green line, and get classified as positive. And because it has moved along the improvement dimension, it would become a true positive. So like if we pick this green line instead of the blue line, we would get 4 true positives instead of 3. Okay, so yeah. Okay, and we will consider the batch setting here. And like there is a lot of work in the setting of combining improvement and gaming. I'm just mentioning a few of them here. Okay, so I'll like we consider 2 models. One is linear and the other one is general discrete model. So I will just briefly explain the models and like mention some of our results. Okay, so in the linear model, each example is in high dimensional space and the labels are binary. And then the true decision boundary is linear, but the learner's classifier can be nonlinear. And then each feature is gaming or improvement. We want to incentivize the features to move along the improvement and become truly positive instead of gaming and not changing their true qualification. All right. Okay, so like if you consider this example, there are 2 features, improvement and the vertical feature is gaming. And then the cost of moving along the improvement dimension is twice the cost of moving along the gaming dimension. So it's easier to game. Okay, and then this linear line is the true classifier f star, and this blue region is the region that the mechanism designer would pick. Okay, and then we have 3 examples. These x1 init, x2 init, and x3 init. These are like the initial locations. Okay, so like if you look at x1 init, in order for it to get classified, like it wants to try and reach to the blue region, right? So it would go to the x1 perceived location. Like that's the cheapest way for it to reach to the blue region. And then, but like its true location would be at x1 true, because the rest of it is gaming, and gaming does not really change the true qualification, right? So at the end of the day, like although it's been perceived at x1 perceived location, but its true qualification would be as if it was at the x1 true location. And then this is fine because x1 true is on f star, so it's truly qualified, right? So basically we're making x1 in it to be truly qualified. And similar for these x2 and x3, because like x2, all it does is just to move along the improvement dimension and like pass f star, so it would be truly qualified, and x3 is already truly qualified. So yeah, we can, so this is an example of a nonlinear classifier that the mechanism designer can select. And okay, so just some of our results are that, okay, so there's a question. Oh, I see. Okay. So what is the relationship between improvement and true qualification status? Okay, so the true qualification would be based on f star. So whether like there are above f star or below f star, so that would give the true qualification status. But like improvement is like some of the features are improvement, some are gaming. Okay, and then so like the moving along the gaming dimensions does not change the true qualification. So it's like you may see some xi perceived, but you would project it under improvement space and see how much it would have moved with respect to the improvement space, and then you can see whether it has passed f star or not. If still, it would become truly qualified. Okay. All right, so some of our results are like in the linear model. So first, if there are only 2 dimensions, we can efficiently find a classifier that maximizes true positives subject to no false positives. And like we can just use a greedy algorithm to get that. And then like when we go to general dimensions, it becomes NP hard. It becomes even NP hard to determine if we can make everyone to become true positive and subject to 0 false positives. And this is using the hardness results for set cover. Okay, so but this one is that like if there exists a linear classifier in general D that incentivizes everyone to become true positives, we can find that linear classifier using linear programming. So this is just some of our results in the linear model. And then, so I will briefly talk about the next model, which is a general discrete model. So here.
Sorry, Saba, can you go back?
Yeah.
One slide.
Sure.
Yeah, I guess I'm a bit still confused about what is true qualification here. So you're saying that true qualification is decided with regards to F star, but really F star is taking into account the gaming element as well. So if you game more, you can improve less and be qualified, whereas, you know, the two seem interchangeable in this example. So should I not consider only the improvement aspect as true qualification for individuals?
Okay, so you can see my pointer, right?
Yeah.
Okay. All right. So for example, like this X1 in it, right? So in order for this one to reach to the blue region, this is like the cheapest possible way to reach the blue region, right?
Mhm.
But like, so what we're saying is that like the gaming dimension does not matter. So this distance doesn't count. All that counts is like moving along the improvement dimensions. So all it counts is that it has appeared here. So this would be the true location. And this true location is passing F star. So it becomes truly qualified. So the true qualification at the end of the day is with respect to F star, what we are saying is that like this modification does not take into account moving along gaming dimensions.
But I guess I'm still confused. So if you take X1 in it and you game it and you go, over to the top, you can improve less and still become qualified. Or you can just game and become
But you
qualified
cannot
by just
reach.
gaming.
Okay, fine. But like the mechanism designer is selecting this blue region, not F star, right? This is what we are selecting this as the decision maker. We're selecting this blue region. So if it moves like upward, then fine, you can move upward as much as you want, but you will not reach the blue region. And then like if you move like this to reach the blue region, this is not the cheapest possible way. This is the cheapest possible way. So it's like I'm shaving off these rectangle. So I'm shaving off these triangle to discourage X1 from gaming. Similarly here, I'm like shaving off this triangle so X2 would not move upward. It would be too costly for it to move upward. It would rather move horizontal and reach, and therefore become true. Yeah, right.
Thanks.
Yeah, of course. Okay, so in the general discrete model, okay, so the space is discretized. So what we're having is like a set of agents on the left-hand side, a set of target points on the right-hand side, instead of a whole space. And then like there's an underlying bipartite graph, and then each edge can be blue or red. Blue means improvement, true improvement. Red means gaming. So if like an agent moves along a blue edge, it would become truly qualified. And we want to encourage moving along blue edges and discourage moving along red edges. Okay, so the mechanism designer's goal is to select a subset of the right-hand side. So the subset of the target points or right-hand side and select them as positive, such that if each agent selects the cheapest edge to the selected points, it maximizes the number of blue edges taken subject to a few red edges. Okay, so for example, here, if the mechanism design is only picking 1, 3, and 4, and let's say we're in the setting that C11 is more expensive compared to C12. So let's say that the mechanism designer is picking 1, 3, and 4, then like the agents are gonna pick these 3 blue edges, and like no red edges are taken. Whereas if the mechanism designer selects 1, 2, and 4, then this agent 1 would select C12 because it's the cheapest compared to taking C11. So 1 would select a red edge. So at the end of the day, we will be left with 2 blue edges and 1 red edge. Okay. And then so some of our results are that maximizing blue edges subject to no red edges is solvable efficiently. Just need to do greedy. But like if you want to maximize blue edges subject to at most k red edges, it would be NP hard. Okay. And then we can also like add some learning component to it. So suppose that agents on the left-hand side are coming from a distribution D, And then like there are two learning models. The first one is a full information model where like if we pick a sample of agents on the left-hand side, so the target points are fixed, okay? Like what is coming from a distribution is agents. So let's say we pick a sample from agents and the target point is fixed. In the full information model, we would see the complete underlying graph. Whereas in the partial information model, we can just select a subset of the right-hand side, and then we can only see how agents would react to it, like where agents would end up, but we would not see the whole underlying graph. Okay, so we have these two learning models, and like the goal is to find a subset of the right-hand side that gets a lot of true positives, and by a lot, I mean up minus epsilon, and at most epsilon false positives, where opt is the maximum possible subject to 0 false positives. So this is the learning goal. And then like we can achieve the goal in both a full information and partial information model. So this is just on the learning component. And then, so I'll just move to the last part and it will be short. So in the last part, so here we are in a one-dimensional space, and the goal, like agents can only improve. There's no gaming component here. Here, what we want to do is to incentivize agents to move and improve, and we want to do it in a fair way. Okay, so let's see. Each agent has a one-dimensional component, which is their skill level. And then like our goal is to come up with a set of targets such that when agents move to the closest target within reach, so they have a budget for moving. They can move it at least for a distance of delta. So we want when the agents are moving to the closest target within reach, the total distance travel, which is corresponding to the total improvement, it's maximized. Okay, this is it. And okay, so and yeah, we have like we can come up with at most k targets. Okay, so the resources are bounded and agents can move for at most delta, and we want to maximize the total distance traveled. Okay, so this is easy. We can just do dynamic programming. But let's see what makes it tricky. So one piece of closely related work is this work by Diane et al. On fair portfolio design. So their goal is to is like they're again on a one-dimensional space. They want to come up with a set of portfolios when like each agent would move to the closest portfolio on the left-hand side. And the goal is to minimize the total distance traveled because it's corresponding to the total risk. So they have a minimization problem. So the setting, so the difference is that our setting is non-monotone. So that means that, so let's say that, for example, so it means that if we add an extra target, like we are a maximization problem, and when we're adding an extra target, it may increase the total distance improved. So that's why it's monotone. For example, here we have one target, and these two arrows show the distances traveled. But when we're adding an extra target, it's suddenly decreasing the total distance traveled. Okay, but like in this fair portfolio design, their problem is monotone. Okay, so I'm just going to talk about two notions of fairness in this setting. Okay, so let's say that agents come from a set of G groups. Okay, so like one easy fairness notion is max min. Basically, we want to maximize the minimum total improvement across all groups. And this is easy. We can just use dynamic programming, construct the whole Pareto curve, and find a max min solution. But like another notion is that like for each group, achieve approximately the maximum improvement possible for that groups had we assign all the resources to that group in isolation. So if that group was the only group that matters, we could assign all the resources to that group. And what is the maximum improvement possible that we can get? And now in the multi-group setting, get close to that target. Okay, so let's see an easy solution and let's see why it would break. So for example, suppose that we have two groups, A and B. So one possible solution is to assign half of the resources to each group and then optimize for each group separately and then take the union. For example, here we have two agents within distance of delta minus epsilon. So put this target for the left-hand side agent, and then this one for the other agent. But like when we're taking the union, suddenly the right-hand side agent is only moving for distance of epsilon. It cannot move, reach to its assigned target because it's going to the closest target. Okay, so it's like this easy algorithm would break. And like our main result here is that if the targets are at most the number of groups, then, okay, so this is an existential result. We can show that there exists a solution that guarantees each group can achieve poly G times the maximum improvement possible for that group in isolation. And this is like G cubed. Okay. And then, okay, so again, this is an existential result. Like finding such a solution is easy. We can just use dynamic programming, construct the whole Pareto curve, and then find the solution that achieves a guarantee. Okay, so the main result is to show that such a solution would exist. And then, okay, we can also like extend it to the learning setting where there is a distribution over agents. And then we can get some generalization guarantees by this framework of Balkan et al. Okay, and then I'm done. Just to summarize, I talked about these 3 lines of work. The first one was online case, all manipulation. And there are these 2 open questions when the clean data is not linearly separable and get some bounds in terms of the hinge loss of the clean data. And also for the weighted L1 cost with unknown costs. And then the second line was where we having gaming and improvement. And the last part was some fairness notions where we're only having improvement. All right, and yeah, I'm done if there are any questions. Thanks.
Thanks, Saba. That was a great talk. Do we have any questions? I have one question. In the part where you were talking about gaming versus improvement, you meant that the cost of moving along the improvement axis is twice the cost of moving along the gaming axis.
Yeah.
But doesn't that kind of incentivize people to move in the gaming axis if the cost is lower? And like, how does that add up with the fact that you want to incentivize people to move along the improvement axis?
Okay. All right. So yeah, right. So so it's more costly to move along improvement, but like the decision boundary is not F star. The decision boundary is this blue region, right? So let's say that this X1 moves along the improvement, right? Fine, you can move along the improvement, but like, for example, if you do something like yeah, move, like if you just move along the improved gaming dimension, you will not reach the blue region, right? And then if you do something like this is not the cheapest way possible. This is the cheapest way possible. So the point is that like I'm shaving off this triangle for X1 to discourage X1 from gaming. Okay. Similarly, I'm like shaving off this triangle to discourage X2 from gaming. So at the end of the day, the decision maker comes out with this blue region, not F star.
Okay, so if I imagine a negative example right under X1 true, like there is a negative example, then that agent can go up along the gaming axis and be classified positive.
Yeah, that's
so
right.
We're not protecting against like those X1 negatives that are under, for example,
Yeah,
X1 true.
that's true. Yeah. So it's like in a batch setting, we would see like the agents, and then like you need to shove off the right regions for each example to like discourage gaming. Like if there's an example here, you would probably need to shove off like a triangle like this to shave off.
I see.
Yeah.
All right, thanks. Are there any more questions? All right, thanks for the great talk, Saba. Yes.
Thank you.